Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is medium voltage and high voltage circuit breaker testing beyond timing and travel measurements. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Volney Naranjo, Senior Applications Engineer. Also, to assist with the question and answer session, we will have joining us Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thank you so much for joining us today, Volney.
Good morning, Michael, and to all the audience, and thanks for the introduction. Thanks for Daniel participating as a panelist. And today's topic, we're going to cover several aspects. We're not going to go in too much detail about the technical aspects. We're just going to do an introduction to the different things that you can do on a circuit breaker, medium voltage and high voltage circuit breaker, beyond the conventional timing and travel measurements on a circuit breaker. So the agenda that we have for today, we are going to talk about conventional circuit breaker testing. We're going to discuss the basics or how it operates and what you get from that test. And then we're going to discuss how to make this test safer and faster. There are some hazards that are involved with conventional timing, and there's a lot of procedures and activities to do to be able to do the test. So we're going to discuss how to make it safer and faster. Then we are going to discuss different tests that can be performed to obtain more information from the test and from the testing activity on a breaker, and some advanced techniques and other techniques to get to be able to test a breaker. Sometimes it's not that easy to test a breaker, so we're going to discuss that as well. And that's the agenda for today. Let's start with conventional circuit breaker testing. First of all, what breakers are we talking about? So we are talking about breakers that are classified or that work above 1 kV. So the very first one to think about is the typical metal-clad circuit breaker that I'm showing here in this picture. I'm showing the rear part of the breaker, a vacuum circuit breaker, 4160 probably. Then we have another, I think this is a vacuum circuit breaker, and it is installed in a distribution substation, probably 69 kilovolt or probably lower. Then we have here a bulk oil circuit breaker. There's a each phase has its own tank with a big volume of oil. These are not that common anymore. At least they are not being manufactured anymore. They're still common in the US, and as they are failing or they're getting to a point in live service that might not be beneficial to keep maintaining them, they're replacing them, and they're replacing them with SF6 breakers. There's also oil circuit breakers, low or minimum oil volume. I don't have a picture here. They're not common, that common in the US, but they look very similar to the SF6 live tank breakers. So here we have SF6 breakers, live tank to the left, dead tank to the right. Probably this one is one of the most commons here in the US. And then we have another big SF6 breaker, 500 kilovolts or probably higher, and independent pole operated, one mechanism for each phase. And in the world of the medium voltage and high voltage circuit breakers, we also have GIS substations, gas insulated. And of course, these ones have a circuit breaker as well, and it is subject to test as well. You can test these breakers and as any other electrical equipment or breakers especially, they may fail at certain points, so it's important to do maintenance testing. And in the GIS world, you also have medium voltage GIS substations, which are starting to be more and more common nowadays for distribution systems in like small facilities, industrial and things like that. So we are going to see different aspects related to these breakers or different tests that you can perform on all of these breakers. Second, well, what is a circuit breaker analyzer? Well, a circuit breaker analyzer is kind of an oscilloscope, a very advanced oscilloscope that you have several channels that will have input for analog signals or digital signals, and it also has a timer. So the basic principle of the operation of a circuit breaker analyzer, it will you will send or from the instrument you will send an operating command, or it will close a contact, and at the moment that the close or the signal is sent, the timer starts, and as soon as any of those analog channels, depend how you have program or set up the test plan, it will capture information, and at a certain point when something happens, the timer stops. So it's a very versatile equipment. It has multiple channels, and depending on what you have or what manufacturer you use, you will have more or less channels and more ability to perform all of these advanced tests that we're going to talk about today. So what is circuit breaker testing, or how do you do the test setup? How you set up the breaker for testing? So in this case, I'm showing a breaker. This is a dead tank circuit breaker. It is a independent pole operated breaker. So you have three mechanisms. This is the box or the control box for mechanism 1. This is 2. This is 3. And this other box here is the control box. So where all the interlocks and all the commands and everything arrives and goes to the breaker. So so also here I'm showing that the breaker is I'm showing only one phase, current circulating through one phase. And the very first thing you need to do to run the test is open the breaker, because you need to connect to the terminals of the breaker. So you need to open the breaker and isolate that breaker. So breaker is open, and this is a very important aspect. Just keep this first part of this very first step of the procedure in mind for one of the other tests that we're going to discuss. This action is kind of wasting or letting go a lot of very good information, and that's why the first strip is developed or is a very good test to use. So first thing, you open the breaker. Second thing, the breaker has to be isolated. So if the breaker is in the surroundings of overhead lines next to other breakers, there's going to be a lot of induction, and there's going to be a lot of magnetic coupling, capacitive coupling, and the breaker has to be isolated to create a safe zone, and then the breaker has to be grounded on both ends. Both ends of the breaker have to be grounded. So at this point, you have already created a safe zone for testing, and everything or all the connections have to be done in this area to maintain the safety. We're going to talk more about that later on. Once you have the breaker in this condition, now you can go and connect the test instrument. So you take out your test instrument. The first thing, you ground the instrument. Another very important step in the procedure. And from that point on, you need to make connections from the instrument to the breaker. There's several things that you have to connect, or three main things to connect for a conventional timing and travel measurement. First of all, you need to control the breaker. These breakers that we're talking about, they do not operate on their own. They need an external command to operate. So the instrument, the test instrument, the circuit breaker analyzer is going to act as the simulation device of the external command. So the analyzer, the circuit breaker analyzer, is going to simulate the close, is going to simulate the trip command, and that's why you need to connect to the control box. Next, you have the main purpose, one of the main purposes, to time the operation of the main contact. So you need to connect a set of leads to each pole of the breakers, to the poles of the phases of each side of the breaker. So this is represented here in the orange line. Control is in the purple line. And then if you are measuring or going to get the travel or the motion of the breaker, you need to connect the transducer. So a very schematic representation here. In blue line, we are going to the control, or to the mechanism, the box that contains the mechanism of the breaker for this specific pole, and we are going to one of the channels of the circuit breaker analyzer. So these will replicate for the 3 phases in the breaker. And if you have a gang operated circuit breaker where you only have one mechanism, well, there will only be one connection of the blue lines here. So now you have your connections, all what you need for the conventional testing. And the next step is to unground one side of the breaker. And the reason to do this is because the way conventional timing is performed. Conventional timing is performed by continuity detection. So if the breaker operates and closes, these leads, these orange leads here, they are applying a small voltage, and depending on the manufacturer of the test instrument, you will have different ways to handle that signal, but in essence is a signal to applies a small voltage, and as soon as continuity is detected, that's when the breaker or the instrument detects the timing of or the operating time of the contact. And I think I went ahead of myself in the slides, but I have another slide showing that. So, but the main thing here is that continuity won't work if you have one of the sides grounded. Or both sides grounded, sorry. So you need to remove one of the grounds, and now you can see that when the breaker is open, this side of the breaker is going to be grounded through the test leads and through the instrument. So this creates a condition that might affect the readings, or might affect, or might be a safety hazard. So here is the breaker ready for testing, and as I was explaining, conventional timing works. The instrument will put a voltage here, and as soon as this breaker is closed, it closes the circuit, and current will circulate. And as soon as that current circulates, you can see, or you can calculate a resistance. So what conventional timers do is that they have a threshold set up or programmed, and whenever that threshold is met, then the software or the algorithms define the moment that the breaker closed or open. So in this case, I'm showing the graphic representation of a closing of a breaker, and you can see that the thin line means that the breaker was open, and at this instant, phase A close, B close, and C close. So, and that is determined by a resistance threshold. So that is conventional timing. What operations you do? Close, open, which are the 2 basic operations, and well, the rest of the operations are simulations of conditions that the breaker could be exposed to during real life operations. So close open is the representation or the simulation of a condition in which the breaker closes, but there's a fault in the line and the relay trips the breaker immediately, or there's a trip command as soon as the breaker closes. So and it's called trip free. The other 2 operations are basically the simulation of a reclose. So some breakers are set up, or they are built or installed to be able to have the ability of reclose the circuit, and they could be an independent pole operated reclose, like reclose on each phase, controlled separately, or it could be the 3-phase reclose. And the last one, the open close open, is basically a simulation of a reclose where the fault is still there. So depending on what the breaker is set up for and installed for, you would do these operations. The 3 mandatory operations are close, open, and close, open. And what you get? Well, you get, first of all, because you are connected to the control, you are connected to the coils, and you are sending commands to those coils to operate, you get the coil current. So this is the representation of the coil current. And then you would get another set of results. Here, you see the schematic of the contact closing. You see these 3 thin lines here. That means the breaker is open, and this is the moment that the breaker closes, and it's represented with thick lines, and then the breaker open again. And if you follow this curve, this is the motion curve, the travel curve, and from that curve, well, you can see the breaker was open in open position. The top part of this curve is the closed position, and here it open again. And while the breaker is moving, it will have some characteristic spots or situations. So the breaker will have an over travel, will have a rebound, will have a portion of the curve where it will deaccelerate when it is open. So all of these parameters can be calculated from these results. That's what you get from a conventional timing. And it's a lot of information, but there's more things that you can do in the breaker. There's more things that you can test, and more advanced tests. You can find more find information about the breaker with other tests, and that's what we are going to do. A quick overview, what you do with this timing and results. You compare the close and open time to the circuit breaker manufacturer manual. IEC provides some criteria to evaluate the difference between the poles or between phases and between the poles when you have more than one break per phase in the breaker. And also you would like to compare the if there's a pre-insertion resistor in the breaker, you want to know if the pre-insertion resistor is operating correctly in the times that are supposed to be working. And you may also want to connect the auxiliary contacts. I didn't show that, but you also can time the auxiliary contacts of the breaker, and especially if you have a breaker that has an XY relay, anti-pumping relay. And you may have situations in which the breaker is operating normally, or the breaker, one of the operations is slower or faster than the other one, or than expected. So here we have a table of the reasons. We are not going to the details today, but it's for a quick reference when you get the information. So that is conventional timing. Probably spent a little bit more of time than I wanted, but I think it's very good to talk about these conventional timing. And then let's see how to make this test safer and faster. So we discussed, or I mentioned that for the test, you have to unground one of the sides of the breaker, because the way the test is performed is with a continuity measurement. You're applying voltage here and measuring the moment, or determining the moment that this contact closes with the resistance threshold. And well, you are working in a substation in a place surrounded by overhead lines, and you could have accidental re-energization of the installation. Not supposed to happen, but well, that's what happens with accidents. They are not supposed to happen. And lightning strike, you are very close to the line that is coming, and you could have a lightning strike very far from the place you're testing, but it can come to the line, through the line. So also you are next to overhead lines, and these can induce currents, magnetic coupling, and this might not be a safety hazard, but it may affect the results. And if you have an instrument that it's not capable to handle that magnetic induction, or magnetic coupling, then you're going to have results with problems or not accurate. You also have capacitive currents, and this is because the overhead lines, and this is the one that it's more concerning. These will induce currents in your cable, in your testing cable, and it is very common to see problems after or situations after you finish testing. Sometimes we are under pressure because of the time constraints that we have nowadays with an equipment being out of service for testing. So you've completed the test, everything went fine. Now everybody starts disconnecting things, and if the ground is not in place, and somebody disconnects these leads from the instrument, not first from the instrument, then all of these induction, now it's going to be at the end of that cable, and you can see burns, or you can see equipment damaged because of that disconnection. So the very first step when finalizing a test, or whenever you're going to handle leads, again, it's to ground this before disconnecting. So grounding or timing, conventional timing, represents that you have to ground, connect leads, and then after finishing, you need to connect ground again to be able to go ahead with the procedure of the disconnection. And of course, we're talking about substations of high voltage or extra high voltage. Medium voltage also imposes a hazard, but if we're talking about metal clad, well, things are different. But it's very important to consider these. So there's some hazard involved in this, and because of all of these, you could have electrocution, burns from arcing, or secondary injuries, because probably the electrocution didn't do anything, but it definitely trips you off the ladder or of whatever you are. So it can generate safety hazards there. So how to make this safer, and in the process make it faster? So the big thing here is the grounding. So test the breaker with both ends grounded. That is actually in some IEC documents, some IEC standards, that is a requirement. And there are exceptions to the breaker testing because, of course, conventional timing doesn't allow you to do that. However, technology has allowed to generate new techniques, new testing techniques, and that's what we are going to discuss here. Dual ground testing, and we can do that with dynamic capacitance measurement instead of the continuity measurement with the resistance threshold. Very similar concept, but instead of looking at the resistance change, we are going to see the capacitance change, or the change in current due to the change in capacitance. So let me put a modeling here of this breaker, or at least one of the phases of the breaker. You can see here the modeling of the ground. So this is the groundings that we have on both sides in green. And all of this tank, all of this section is represented here by the dotted line. And inside that, we of course have the contact that will move to open or close the breaker. These two contacts are basically two plates, and those two plates are inside of an insulating medium. And it could be SF6, it could be oil, it could be air, but it is an insulating medium. So two plates in an insulating medium is a capacitance. And as the moving contact of the breaker displaces to close the breaker, to open the breaker, means that capacitance is changing. So that's why it's called dynamic capacitance measurement. The rest of the modeling is the inherent resistance of the conductors inside the breaker, inherent inductance, very small, but there's going to be a little bit of inductance there. So in the end, this is an RLC circuit. And when you have an RLC circuit, if you connect another circuit, another RLC circuit that can couple to that circuit, and you inject a signal, a variable signal, there's going to be a point where you can find a resonance point. And resonance point means the point where you have the lowest current circulating through that circuit from the source that you are connecting. So if we close the breaker and we apply a variable frequency current, and we change the frequency until finding the lowest current point. Means that we are tuned to this circuit and we are going to have the lowest current. So now that you have identified a lowest point, now if you operate the breaker, as soon as the breaker opens, now the circuit is not tuned anymore, and that current is going to be higher, as I'm showing here. So anytime you operate the breaker, current will change. And that, if you're monitoring that current, instead of monitoring a current that goes from 0 to something, now you're going from one value to another value, lower to higher current, and that is the way that you can detect the operation of the breaker. That is dynamic capacitance measurement, and that is a technique that can be used to time the breaker. As you can see here, this circuit and all of these variable frequency source is represented by one accessory here in the connection. So the connection is very simple, and it doesn't add more time to the test, but you're going to increase the safety and you're going to increase the speed or the efficiency during tests, because now you don't need an authorized person to remove these. And when I say authorized person, is because sometimes it has to be a very specific crew, and sometimes they have to talk to control to be able to disconnect, to do any procedure. So that represents time. If you don't have to do that, you just go there, ground, connect your leads, and you don't have to talk to anybody else until you finish your testing. So that increases the speed of the test and of course the safety. The other big advantage is that you obtain the results in the traditional way that you get the results from timing. Conventional timing, because you are monitoring the same thing. You're monitoring a current, and you can even see those little bounces that may happen if there's any kind of lack of pressure in the contact, in the fixed contact. So it is a very practical way to see the result. There's another technique to do dual ground, that is dynamic resistance measurement, but that is not as accurate as the DCM test, and you won't have the results in the same conventional way. So DCM is a very practical way to do it. It improves safety, efficiency. You don't have to do all of these steps when doing the testing, and the result is exactly the same. So there's no way you can say that this was done with capacitive or conventional testing, DCM or conventional testing. And the technique allows you to apply this for other situations. So there's more applications that you can test with this accessory or with this technique. First, generator circuit breakers. So disconnecting, you want always to have one side grounded, and having this side ungrounded is not the safest thing. Again, you could be, you are exposed to all of those situations. So the best thing is to have this side grounded. And disconnecting this generator, it's not the most efficient thing, or not the greatest activity you can do. It represents a lot. There's a lot of links there, and you need to connect, you need to torque those. Sometimes getting access to those links is very difficult, and it might represent a day worth of work. So to be able to test probably a 3-hour test, that you're going to spend one day prior to that and one day after the testing disconnecting and connecting back the generator. So not very fun to do. Also, GIS testing. You can test high voltage GIS with this technique. The challenge with the GIS substations or switchgear is that you don't have access to the terminals of the breaker. The only access is through the grounding points. And to be able to get access to that, you need to disconnect the grounding links. Again, not safe because the circuits next to that one that you're testing, it's going to have a lot of capacitive coupling with the point. So you are introducing a safety hazard. So with this DCM technique and one more accessory, you can test, and you can test very easily, very fast. And other difficult applications like a transformer, for example, sometimes you are going to be far from the breaker, and you can see here 25 meters, something around 75 feet. You might end up getting not very good results because of the distance and again, a grounding problem. So you can kind of not worry about the breaker being grounded with this technique. Okay, that is in regards to safer and faster testing. So really, we are doing the same conventional time or the same time test, timing and travel, but you are just doing it a different way to improve the safety and the efficiency of the test. Next one is first trip. So this is a diagnostic test. This is a test that is performed to get probably similar type of information that you get when you do conventional timing, but it's at a different moment. So let's see, why first trip? So the breaker, usually the life of a breaker is to remain close or remain in close operation for a very long period of time. Usually breakers do not operate that often unless they are in like a distribution circuit or something like that they need to reclose, but usually breakers remain in close position for months or even years. And well, this creates a situation in which the breaker gets might get a little bit rusty. It might be very well lubricated, but it is exposed to very harsh conditions, kind of constant high temperature or constant low temperature, or temperatures that change drastically from night to day, or it can be exposed to situation, a lot of contamination, so industrial facilities with a lot of dust, or substations in areas that it's windy and it blows a lot of dust. So all of these things can get into the mechanical elements of the breaker, and they can affect the lubrication or the condition of the metal. And I always do the comparison of these like you are driving a car for 8 hours. If you make a stop and you try to go and run, well, if you're young, you may be able to do that, but if you are not in good condition, you need to do a little bit of warm up. So that first operation, that first walk after so much time being in rest condition might not be or it shows your real condition actually. So when the breaker is prepared for conventional testing, this first operation is the very first thing that happens, and it goes unmonitored. Nobody monitors these tests, and that's why I kind of ask to keep it in mind. The very first thing we do is open the breaker, and nobody is measuring that. That is called the first trip. And now that after you connect the leads and you're ready to test, now you probably have done 1 or 2 more operations in preparation for the test. Now the breaker improves. That is like the warm up, and now it's not anymore rusty, and the mechanical links and everything is going to be good. So the performance of the breaker when you do conventional timing shows very good, but in that very first trip, you could be discovering a lot of things that may not be critical now, but they are starting to show up. So first trip that was developed for that. It's a testing opportunity to measure the trip coil during the first operation of the breaker. So that is first trip. And the purpose is that, so it's we have this coil, and you can do first trip and first coil and first close as well to see the condition of the coil. So the idea or the purpose is to record the very first operation after a long period of rest. And the main purpose is to collect or to record the coil current and the control voltage. And here, this is what you get. This is the typical trip coil current. And if this is the first trip, the idea is that you're going to compare these to the same current measurement in a previous time, like when you commission the breaker or any time that you tested conventional timing, but under the good condition of the breaker. You know that the breaker is good, so you may end up having something like this. So that is the purpose of the test. Measure the first trip and then compare to a previous measurement and see the differences, and especially some specific points that I'm going to show in the next slide. So benefits: you record real world operating conditions. It's a very simple and fast connection. You just go to the control box. You're going to see that no operation goes unchecked, and you may not need to pull the breaker out of service. So what companies are doing is that they just perform first trip tests, and with the results of that first trip test, then they schedule the maintenance on the breakers that they see that are starting to have some problems from this test. So this is a test that is used to prioritize the actual maintenance testing, conventional testing, and other things in the breaker. If everything shows good here, they just leave the breaker alone for more time, and they are saving in maintenance and activities, and they can concentrate in other assets. So testing setup, and I have testing setup 1, in which we are only recording the first trip and the control voltage. There's another one that you can get more information, and you can even time the breaker. So let's go with the first one first. So here I changed the breaker. It's a SF6 breaker, gang operated, dead tank, and again, we connect only to the control box. So I'm highlighting here where you are going to be doing the connections, and well, you look into the connection to the control circuit. You look for the trip coil. In this case, we see that trip coil. Where's my pointer? Here. So 52T is the trip coil. So we are interested in the current that will circulate through this branch when this remote contact closes. So this operation, or the operation of the circuit breaker, will be commanded from the control room. In this case, the command is not going to come from the instrument. So we don't need to do any actual connection to the trip coils or to apply a signal to this circuit. The signal is going to come from the relay from the control room. So the very first connection is a CT that is going to monitor the current in this circuit. Then we want to monitor the voltage. So we need to connect to the positive and negative, and this is important because this gives you information about the actual DC signal from the control or from the substation. And one more connection that is needed is a trigging. So the instrument, the circuit breaker analyzer, needs to know when the breaker is receiving the signal. So this connection is just to monitor for that signal that is coming from the control. As soon as there's a command here and that command gets here, the instrument will be activated to record everything. That timer that I was mentioning at the beginning will be activated, and all of the analog channels will be measuring whatever they need to measure, the current and the voltage. So that is the first connection. Now, you can also connect to other auxiliary contacts if you want to measure the timing of the auxiliary contact. So that is an extra thing that you can get from first trip, not necessary for the basic measurement. So that is one setup. The other setup is basically includes more connections or more information. We'll collect more information. So in this case, what we are going to do is to focus on the primary circuit. We are not going to connect to the primary circuit, but there are CTs in this circuit in the load side of the breaker. And so basically these CTs are represented here. And what happens is that as soon as the breaker is open, current will be interrupted here. So monitoring that current gives you the timing of the breaker. And it's not going to be the same accurate measurement that you do when you do it with conventional timing, but it's going to give you a very good approximation of the actual timing of the breaker. So we go again to the secondary side of those CTs, and those go through the control box. And in this case, we are going to connect CTs to each phase, and that is going to measure the line current. And everything will show like this. This is the when you use the two connections or you do the two setups, then you're going to get the current from this CT. You're going to get the voltage from this connection, and this one you can see how the voltage drops because of the load that the coil imposes into the DC system. And the third result, main result that you get, is the current. So you see the sine wave here, and at certain point that sine wave goes away, and that means the moment that the breaker closes. And you see that definitely it happens after the operation of the coil. And well, motion is not measured here. You don't want to put your hands in that breaker while it is energized. It may operate, so definitely motion is not recommended unless it is a transducer that is previously installed there and permanently installed, that you just need to connect a cable. So this is what you get from the first strip. Now, what is analyzed, or what are you looking at, or what are the interesting points here? In addition to the voltage, well, in the coil current curve, you are interested in the peak current. That means when basically the coil becomes a short circuit for the DC circuit, you will get a peak current, and that current could change, and that represents the changes in the coil. Then you want to know this other peak. This peak is the moment that the armature, the plunger, starts moving. So there's an armature inside the coil, and as you energize the coil, there will be an electrical field there, and it's going to generate or cause this plunger to move. And that plunger, what will do, well, it will happen at a certain peak current, and it will happen at a certain time. And then when that plunger or armature stops and it hits the trip latch, then it will change the current, and that happens at a certain time. So that is also important. And whenever an auxiliary contact opens to de-energize the coil, you will see that the current starts dropping. So that as another point of interest, and the time to the end of the operation of the coil, and no more current circulating through the coil. All of this is what the circuit breaker analyzer will give you, and it will calculate parameters from here. And well, one thing that you can calculate is the voltage drop in percentage. And you know that coils have a minimum operating voltage. So if the voltage is dropping too much, you can start detecting that. So it's indirectly a test on the DC system. And in the analysis of the coil current, well, you may have these, so you know that you have the armature peak currents and then the coil peak currents. And there's going to be differences in those currents and differences in the time where those events happen. And comparing those times, or you could have no armature movement, and it goes directly into a short circuit. So comparing or analyzing all of these points will give you the ability to detect problems in the trip latch system or the link system of that trip latch. you could end up finding problems with the coil winding, coil armature, or low voltage issues or wiring issues. And all the operation of the breaker happens because this coil operation. So anything that happens from that point on will be affected because of these delays or these operations. So first trip provides you a very good way to analyze most of the operation of the breaker. It provides real life trip time, and it can reveal lubrication or corrosion problems. It is a very quick test, and if the breaker can be reclosed immediately, a control can send a reclose operation. It may not show up for the system as an interruption, as an outage. So it's a test that goes unnoticed, and you don't need to affect the system. That is one of the great advantages. And you can do as found and as left test with these, so you can compare for the future. And mainly the main use of these tests is to determine where offline maintenance actions need to be focused. You can reduce the maintenance activities, the schedule or regular maintenance activities, with these maintenance based condition based oriented maintenance activities. So that is in relation to first trip. Then motor current. This is a very simple test, and it's been very common. Sometimes we just do it with a CT, but this can be brought to the circuit breaker analyzer as well. And well, what is the motor? So circuit breakers that have spring charge or spring mechanisms, this spring needs to be charged. So you need to store mechanical energy for the breaker to operate. And well, these springs are the ones that store that energy. So at certain point in the operation, the breaker or the spring needs to be charged, and there's a motor for that. This motor is fed from the internal power supply of the substation, and any malfunction in the mechanism that is coupled to this motor will affect how the current of the motor looks. So if the mechanism is getting stiff, or there's a problem with the springs, you're going to have some changes in the current. So again, it's something that you can compare. You can look into historic current measurements, and you can determine early detection of issues with the spring. The current monitoring is performed by connecting a current sensor, similar to what we did with the first strip. We connect to that portion of the circuit that feeds that motor, and we operate the breaker for the motor to operate, and we record that current. And the idea is that we observe changes in the shape of that current, maximum current and operating time are not exceeded. That's what we're looking for. Usually they will have a defined operating time and a maximum current. So here we have the graph showing the inrush current of the motor in blue, or the current of the motor in blue, and then we see the inrush current, and then it comes down and it starts compressing the spring. Of course, the current level increases, and at certain point it finishes, and the mechanism releases the latch and the motor stops. And we are also monitoring the voltage here, and we are getting the difference. So in this case, this motor took 13.5 seconds to charge. And then you want to compare these to whatever you have as a reference. Motor peak, if the motor current is too high, or the motor charging time is too long, it could be indication that the charging mechanism requires a more force than normal. So something is affecting the mechanism. So you could start looking into some maintenance activities in the future for that. You could be missing lubrication there. Or if the current peak is low, means that the spring might not be as strong as before, and it could be broken or fatigued. So just from the current measurement, you can get a lot of information on a motor. This is also something that is used for load tap changers in transformers. Totally different topic, but it's exactly the same concept. You're looking into things that could affect the operation of the motor, and of course they are related to whatever they are coupled to. So that was in relation to motor current. The next one is called dynamic resistance measurement. This is something else that you can do with breakers, and this one is more oriented to SF6 breakers. SF6 breakers, the contact system, the contact where current passes through when the breaker closes, the moving and fixed contact is composed of actually two elements. The main contact, the one that is going to carry the main current, or the current that passes through the breaker, but that contact is in parallel with another contact that is called the arcing contact. Every time a circuit breaker operates under load and under fault conditions, when the contact opens, there's an arc. That arc is extinguished by the combination of three things. One is the speed of the breaker, second, the crossing through zero of the current, and a refrigeration that comes from the insulating medium. But the arc still happens, and the idea with this arcing contact is that the main contact doesn't suffer from that and doesn't get deteriorated. So in this case, we are seeing here the cross section. This section here is the main fixed contact. The other one here is the moving main contact. And here we have the fixed arcing contact and the moving arcing contact here. And we can see main contact here, moving contact, sorry, fixed contact, then main moving contact here. And this rod here is the arcing contact, the fixed arcing contact. And inside this nozzle is the moving arcing contact. So and you can see here from this representation that the arcing contact is longer than the main contact. So what happens is that during the operation of the breaker, the current is flowing through these two contacts in parallel. Now, the resistance of the arcing contact is much higher than the main contact. So in reality, current circulates through the main contact under regular operation. When the breaker starts opening, at certain point, the main contact opens, but the arcing contact does not open yet. So all the current is transferred to the arcing contact. And then the next step of the operation is that the arcing contact opens, and now all the arc is going to happen here. So in the end, what happens is that these two arcing contacts, the fixed and the moving arcing contact, will deteriorate, will erode with time. And there might be situations in which that contact needs to be replaced. To the right of the slide, you see a graph from one of the manufacturers where they show two different types of their breakers, and you can see how many operations will have the life of that contact under short circuit conditions. So you could have, if you have an interrupting current of, I don't know, 10 kiloamps, then that represents 500 operations or so. Or if you have 20 kiloamps, sorry, 40 kiloamps, you may have only 20 operations. Now, operations under fault or current or short circuit conditions are not going to be always the same. So, well, there's this graph and there's some formulas, but really you don't know when the breaker, the arcing contact needs to be replaced. So, the replacement, there's a replacement criteria. In this case, for example, the manufacturer is indicating that if the upper current of the path of the current path fixed arcing contact has been burned, so the distance to the reference surface is more than 6 millimeters, or it is outside of the surface of reference, then it has to be replaced. So what are they talking about? They are talking about this section, and here they see the reference point, the reference surface, and maximum that the arcing contact can go inside, or the wear length is maximum 6 millimeters. How to determine that? well, the easiest way is with a visual inspection, but visual inspection is not, it's not very good because, well, that means a major maintenance on the breaker. And also SIGRE studies show that the breakers fail mainly after major maintenance of breakers. So probably not the best thing to do, and if you do that, then you just replace it, because, well, what you're not going to close or assemble the breaker again without replacing it. So there's testing that can be done for that. Now, conventional timing doesn't, even though it does resistance measurement, as we discussed at the beginning, it does not differentiate between the main contact and the arcing contact. You get no information about the condition of the contacts. The resistance thresholds are not capable to be detected by the test, and there's no way to measure the length. So the solution is dynamic resistance measurement. What is dynamic resistance measurement? Well, it's a combination of contact resistance measurement, the traditional DLRO or Doctor test that we know, but we combine this with the operation of the breaker. So as we are operating the breaker, as we are opening the breaker, we are injecting current and measuring the resistance, and looking at that in time and how it compares to the motion curve, to the travel curve. And what does the connections entail? Well, you need to do the same connections as the timing. So you need to do the timing leads, and you need to do the motion, the travel measurement with a transducer. You of course need to control the breaker, and you need to add one accessory. Now you need a current source capable to inject somewhere around the 100 amps or even higher to be able to get a good resistance measurement. And you operate the breaker while that current injection is happening, and then these leads now, instead of applying voltage as they were doing before, now they are measuring the voltage drop across the contact while the breaker is operating. So when you do that, and as I mentioned before, you can do this test, or this test, you can do it with both end grounded, and you can also see the timing of the breaker, but it's not the best approach. Then what you get is this. This is the result that you get. You get the travel curve here. You see the breaker is closed, and at certain point it starts moving because the coil already actuated, and then the travel go to the open position. While you're doing that, you're injecting current, constant current injection, and this is the result of that voltage drop because of the current. So now you see the resistance. So resistance is very steady here, corresponds to the motion of the breaker. Breaker is not moving, and then at certain point starts moving. This point is where the breaker opens, and the main contact opens. So you see a change in resistance. Then this is the length of the arcing contact, and then this is the moment when that arcing contact opens. So if you transpose or bring this length here to the motion curve, you can calculate the length of the arcing contact. So you are doing actually a measurement of the length of the arcing contact indirectly with an electrical test. Here we see a measurement before and after short circuit. So you can see that this is before the sorry, my bad here. You can see here that the breaker was measured when it was in new condition, and the length is 15.47 millimeters. Then after some operations with short circuits, then the length is 7.07 millimeters. So a difference of 8.4 millimeters. Definitely the arcing contact wears, and it reduces the length, and at certain point is going to be the same length or at the same level as the main contact, and at that point the main contact starts suffering. So no, you can avoid that. This is when the breaker is open, you can see a spare in the worn contact, and you can see the difference here. Very small difference, but it's significant, and you can see that just a reduction of 6 millimeters from a reference point, as one of the manufacturers shows, is critical. Then I have 2 more tests to go. I'm a little bit on the edge of the time, but well, these are not going to take too much time. So the next one is medium voltage GIS breaker testing. So as I mentioned before, what is characteristic of any GIS switchgear or gas insulated switchgear is that there's no access to the terminals, because everything is insulated, everything is covered, and you don't have access to actual terminals of the breaker, and then testing becomes difficult. You would have to disassemble something to be able to test. And I already made reference to the high voltage GIS. Now we are talking about medium voltage gas insulated switchgear. So as per IEEE, they are classified, or they belong to the area, or they cover the area 1 to 52 kilovolts. There's a standard for these GISs, these medium voltage switchgears. It's IEEE C37.20.9. And most typical installations go from 12 to 38 kilovolts typical. They are installed in large cities, below casinos, dense power areas, industrial installations, basically where you don't have real estate and you need small equipment to be able to have a good insulation system. So they put GIS in those. But then you get the challenge that you have no access to the breaker. They are compact in nature, and the primary components are not accessible. And the best chance that you have is underneath the switchgear where the cables access, but in that case you will need to disconnect. So really not feasible for conventional timing without not disassembling the switchgear. So probably not something that you need that often, but for commissioning purposes and for troubleshooting purposes, you may want to do that. So these pieces of equipment, or these switchgear, they have means to, because there's also no visual line to determine if the breaker is open, to confirm visually if it is open or not, other than just the mechanical flag. Then these also have what it's called the VDS, voltage detection system, in which they have a capacitive coupled voltage detection system. That's what it stands for. And this is an access point for checking if the system has voltage or not. So when the breaker closes, there's voltage on these terminals. If the breaker is open, or as soon as the breaker opens, voltage goes away. So if you can monitor that voltage, you can time the operation of the breaker. So that's what can be done with a circuit breaker analyzer. You can connect to this voltage detection system and monitor the time that the voltage appears or disappears. And of course, with that, you need an accessory, basically a voltage conditioner. And but you just need to connect to that voltage conditioner or to that VDS through this little accessory, go to the timing channels of your circuit breaker analyzer, and then of course you need to connect to the control of the circuit breaker to simulate the operations, the close, the open, and all of those that we already mentioned. No, you don't need to clear the breaker. The only thing is that the operation has to be done without load, so that the load has to be transferred to another circuit, but you don't need to take the breaker totally out of service, and you don't need to do any grounding, anything like that, because you're just opening the breaker and closing it as in a regular operation. And if you want to monitor something else like motion, well, you would have to install the transducer previously, or consider that. And of course, you're going to monitor coil current and, for example, auxiliary contacts if you want. Anything else that you do with a regular timing, you could do here. And this same concept can be applied for switches. Well, of course, the instrument has to be grounded. In this case, the results, the graphic results are not going to be as the conventional ones, but you can see that compared to conventional timing, the timing is exactly the same. It happens and you can detect everything at the same time. So it's matter of the algorithm measuring these or determining these closing point. So this is for the close, you see no voltage and then sine wave shows up. And then this is the open sine voltage, sine wave, and then voltage disappears. So that's the way how you can time a GIS, a medium voltage GIS. And the last test, it's a very this test has been there for many years, and it's not so popular, but well, it's something that you can also do with a circuit breaker analyzer. It's vibration test, and it's available, and some manufacturers do it, some entities, some utilities may do it, and it's a very good tool. It's not so easy to analyze, but it's a very good tool. And what it is done with vibration test? Well, it is a direct measurement of the mechanical events in the frequency and amplitude domain versus time. And you can record the mechanical vibration while the breaker, or the purpose is to record the mechanical vibration while the breaker is operating, and while you're monitoring other things in the breaker, like the coil, the timing, the travel, and you can uh, uh, correlate things there and do the analysis with the different curves that you obtain. So you identify timing or any other event changes, not only with the other measurements, but the mechanical vibration. And because the mechanical vibration has an amplitude, as the mechanical condition changes, that vibration is going to change, and you can detect things there probably earlier, in an earlier stage than you would do with conventional timing. So this is a typical characteristic vibration signal at a close operation. There are many identified stages of the motion, and this is an actual test, an actual example. So you can see here that phase A was closed, and at this point it opened. This is the coil current. We know that this peak here is the moment that the plunger starts moving. This is the moment that the plunger hits the latch, and from this point on, the mechanical actuation of the mechanism, closing mechanism, will start. So you can even see that vibration detects the moment that the plunger starts moving. So no motion, no vibration, and as soon as that plunger from the coil starts moving, you can see the vibration here. At this point, it's very likely when the mechanism, before it started moving, the mechanism was released, so a lot of vibration, and then you see the rest of the motion. Now, vibration, you can monitor different places. So this was probably at the mechanism or somewhere close to the coil side. But you can place those accelerometers in different sections that you want to monitor, and you can get 3 or 4 vibration curves on the same operation. So again, that will demand a lot of channels in your analyzer, but you can do it. And of course, we're talking about breakers that are expensive and very important, that you want to monitor all of these. Here you have a comparison of breakers with a breaker with no issues. You can see that the vibration curve, you have 2 colors there, pink and light blue or light green, and then they are almost overlapping identically, so no big changes. However, in this other one, you have a breaker with timing issues. So there's the events, mechanical events are happening differently, and you are looking to compare the difference in time and in magnitude of the vibrations to start analyzing the breaker. As I said, the analysis is not so straightforward. As any fingerprint signal, you need to understand what's going on, and where are you getting this vibration from. Okay, that finishes my technical presentation. I just have a slide to summarize or to bring some bottom line points here. Circuit breaker analyzer is a powerful and a multifunction tool. So different from, for example, transformer testing that you have. If you want to do advanced testing, you go with some instruments, and if you want to do basic testing, you use some other instruments. Circuit breaker analyzer is pretty much everything what you need to do the testing on a breaker. Of course, you need accessories, but you can have a circuit breaker analyzer that will be able to do all of these things, and then you decide what you want to add to your testing procedures. And that is the other thing, that testing procedures and circuit breaker maintenance can be improved. And my main point here is that probably timing, conventional timing and travel measurement may not be the best approach for you. You may have breakers that you would be better doing dynamic resistance measurement, or you may have breakers that are difficult to test, so you may think on something else than regular timing, and this will save you time and all and activities during the maintenance. And definitely circuit breaker testing can be performed safer and faster. That is very important. There are many utilities that are looking at this right now because they don't have time to have a circuit out of service, or they need to improve safety because someone's already have an incident, or they want to avoid an incident, and this is a way to do it. These tests are anytime circuit breaker requires preparation and requires accessory. That's a reality in circuit breaker testing. And well, the important is to be prepared, to know what you want to do. And once the breaker fleet is the same for a particular company, so you know what accessories you need, and especially for the travel measurement, you can define that in advance, and that won't be a problem anymore. And well, circuit breaker testing is a very comprehensive test. As you can see, even from the conventional timing, you get a lot of information. You get information from the coil, from the contacts, and from the mechanism. And adding, for example, motor current, you will make it more and more comprehensive test, and you get a lot of information, and individual components can be analyzed. With that, and last slide is the offering that we have in our circuit breaker analyzers. We have from the Eagle, the one on the left, which is a very simple instrument, a very basic instrument for timing and travel. It can test up to 1 break per phase. But it can also do dynamic resistance measurement. So it's an instrument that looks very simple, but it has one of these advanced tests. Then we have the TM family, the TM 1700 series and the TM 1800 series, where you have 2 breaks. You can test 2 breaks per phase and on with the 1800. Of course, you can do timing and travel with all of them, with both of them in the TM family. You can do first trip and dual ground, and you can do dynamic resistance measurement also for 2 breaks per phase and more. And well, if you are interested in vibration, that needs the 1800, because that one is a modular instrument that you can add different channels at will, and you can configure it depending on the needs. So that's what we offer, and we can do all of these tests that I just mentioned with these instruments. With this, I bring it back to Michael, and well, I guess next we'll be opening the floor for questions.
All right, thanks a lot, Volney. So at this time, the presentation portion of our webinar has officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there is a field where you can also request a quote or a demo of any Megger product. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at us.megger.com/webinars and register for our virtual motor best practices seminar on Tuesday, September 22nd. All right, let's get into your questions. The first one I'm going to direct over to Nicholas Wetterstrand. Nick, when using DCM, is it possible to perform motion testing at the same time?
Yeah, hello. Yes, the motion measurements are made through transducers and can be used both with conventional timing and with DCM. So there's no difference in the method and how you do it.
All right, thank you. Next question is going over to Daniel Carreño. Daniel, how would you practically measure the first trip when the breaker has to be open and locked out and be ready for service? When would you have the opportunity to set up for the first trip since the plant is in operation and then would have to shut down and then be locked out?
So guys, thank you, Michael. Well, actually, the first trip, as the name implies and as Bonnie went over during the presentation, you want to capture that very first operation of the breaker, right? So the connections to the measurement are done directly to the control panel because the circuit breaker is live, it's in operation. As again, you want to capture that very first operation. So the breaker does not have to be open for even, I mean, then if you do that, you miss the first trip of the circuit breakers. Again, the connections are made to a live circuit, and that is why the connections are limited to the control panel. And if you want to measure the currents, the main currents, you have to do it through the secondaries of the CTs of the breaker. So you connect to the secondaries of those CT.
All right, thanks, Daniel. Next over to Nicholas. What is the difference between DRM and DCM for dual ground testing?
All right, I'll try to explain that. First, can I ask, is it possible for me to share a presentation or no at this point?
Sure, I can send you control right now if you are ready for it.
Yeah.
There we are.
Good. So I hope this is up to the screen now.
Yep, we are good to go.
Okay. So it was actually covered a bit in the presentation, but just to go through it very quickly. So dynamic resistance measurement is, as it says in the name, that you measuring the resistance over time, so through an operation. And this was a method that we introduced to the market way back in the 90s. And as Bolny have explained, it's made for a primary function to test the arcing contact length. At the same time, at that early stages, we also realized that you can do timing, both conventional and both sides grounded with this method. However, it has a few limitations, which I will cover in a few slides. The dynamic capacitance measurement, or the DCM, that is something that we invented later, and it's only for timing and dedicated for that, and it's much more accurate, and that's where we released this method of testing with both sides ground, or dual ground as we call it. It's a lighter and simpler solution, and it works on all different kind of breakers without limitations. So I will skip through a few slides. You already saw how the technology works for the DCM, and I walk through to the DRM. We did talk to this as well. So it's simply a resistance measurement when you do it over time. And you get something, this is an ideal graph, but anyhow, you get something that looks like a trace that's going down like this, the resistance changes. So when the ground loop is only connected, so this means an open breaker, you might have something like 3 milliohms. Then you will have the arcing contact, which is a small step down in resistance, since the arcing contact itself, it varies a lot, but it could be like 1, 2, 3 milliohms itself. And then the step down here is very low, and then it's relatively easy to see when the contact closes. However, in the standard, it's referred to that the closing time is when the first metal contact touch is appearing, which is actually this point, not this point, which is very easy to detect. And that is why it's more difficult to get accurate results with the DRM method. If you use that, you will find out on some certain objects, you will have variation of the timing. And as we all know, the timing variations are quite tight tolerances in the specification, the maximum differentiation or diff between phase. So then you eat a lot of this timing, so to speak, with this inaccurate measurement, and that is of course not good. So I hope that explains a bit why the DCM is better and the differences between the methods.
All right, thank you very much. Volny, I'll send control back over to you. And also the next question will also be directed towards you. So once we get that back up on the screen, I'll send it over to you.
Okay, I'm ready.
All right. Perfect. Could you please explain the differences between the two graphs on the first trip and how to know which one is better?
Okay, well, we definitely have a lot of slides on that, but I don't want to spend too much time. I just want to concentrate on this conceptual slide. And the purpose, there's no like a reference, or the main reference will be the commissioning test. Let's say when the breaker is in perfect condition and when the coil current is ideal, or when it doesn't have any mechanical restriction and the breaker is totally new. Then that's what you would use as a reference, and then you would look for these differences to happen. The coil, the current when the armature or the plunger starts moving, and that can increase. That means that the plunger is kind of blocked, or something is not allowing it to move freely, so more current is needed. And then if that is happening, you will have more or a difference in time for that plunger to go to the end of the travel of that plunger. And of course, that may also generate a delay here. Now, there could be situations in which you don't have a delay here, you have just a delay in this side. And that's when you do the comparison of the times, and that will give you some indications of the trip latch, the coil winding, different issues that could be happening with the different elements in the circuit. So these the differences will be introduced by the mechanical characteristics of the condition, or the mechanical condition of the breaker at the moment of testing, and that's what you are trying to find out from the comparison with a commissioning test, or a test that you know is under very good condition of the breaker.
Thank you, Volny. Next, I'll send it over to Daniel. Daniel, when carrying out a first trip test, is it possible to arm the test set and leave the area before the breaker is actually operated?
Absolutely, yes, and that is actually the preferred method, right? Both of the units that you can use to carry out this first trip measurement, the TM1700 series and the 1800, they both have what we call trig in, and that's where you would wire that signal. So yes, you would, like the user or whoever asked the question mentioned, you arm or you start the test, and in that particular configuration, so the unit will wait for that external signal to start the measurement. So yes.
All right, thank you, Daniel. Next, over to Nicholas. Does breaker open time include arcing contact open time? If so, is the breaker open time shorter or longer?
Yeah, thank you for the question. It's as I explained from the previous graph, the arcing contact, if that's available in SF6 breakers, that is included in the timing. So it's the timing is defined from when you have the first contact touch or when you have the last separation, and that is including the arcing contact.
Okay, thanks. Next over to Volney. When we need to test the CB, does it depend on specific signs or time? Because you mentioned the CB may become closed for months or even years.
Okay, well, I would say that this would depend on the maintenance approach or the maintenance program that every entity or every facility has. So some people or some entities will go by maintenance, scheduled maintenance, no matter what, and they would do testing every 5 years, every 2 years. Or it depends on internal policies or procedures. Some other entities will go by the condition, and this is where the first strip comes very handy, that they will just periodically will do the first strip, and they and it's a way to exercise the breaker as well, and you just exercise the breaker, you open it, close it, and when you do that, then you record, and you from that you start determining if the breaker is getting into a situation that requires maintenance, and if not, they won't do any maintenance. And there's other companies that they just let the equipment run until it fails. I've seen those situations, and it depends on the importance of the asset and all of that. So the frequency of test is always an interesting topic in this world, and there's many approaches. So it depends more on the characteristics of the system or the maintenance program, and of course manufacturers, they will recommend certain maintenance schedule depending on the type of breaker and depending on what you have there.
All right, thank you, Volney. Next over to Daniel. Is there a rule of thumb for replacing arcing contact as its lengths get closer to be the same as the main contact?
Thank you, Michael. That's a great question. It's a little bit related to what Niklas answered, just a question before Volney. And we need to understand that when we use the dynamic resistance technique to assess the quality of the arcing contacts, we are not comparing or measuring that length versus the main contact of the same pole. But what you get is, again, a measurement that you can compare either to previous measurements, the same breaker, same pole, or if it's the first time you're testing or you're using this technique, you can compare the length that you get on each phase versus the other two. Right? So again, you are not measuring it against the main contact, but compared to the other phases. In terms of, okay, you get the results, you get the measurements for each phase. There is no rule of thumb that would apply for all breakers. The best bet is to, or the best scenario is that the manufacturer, just like in the slide that Volney is showing, certain manufacturers will actually give you guidance in terms of, again, this very example that Volney is showing is this manufacturer is saying if there is the maximum difference that you can see before this will affect the performance of the breaker is 6 millimeters. But again, that only applies for this very specific breaker. So again, the best source is to consult manufacturer, and if you cannot get that information, again, you can compare between phases.
All right, thank you, Daniel. Next over to Niklas. How valuable is the circuit breaker testing and timing if original test data from commissioning is not available?
Yeah, thank you. This is a very common question, and you get arguments all day around if it's valuable or not, and it is valuable for sure. Even though of course, in an optimal situation, it's always better to have something to refer to and compare to see differences and trend over time. It is still valuable to measure if you don't have any previous data, because you will probably be able to find something around from the manufacturer, some guidance what is specified for this breaker and a timing interval, and you can always compare to that. And if that is not available, you probably have sister units, or you can compare the phases at least. So there are values with measuring a completely unknown object. You will get information anyhow, and can judge if it's healthy enough to stay in service or if it needs some overhaul.
All right, thank you. Next over to Volney. Is DRM required only for SF6CB and not for VCB?
Yes, VCV or vacuum circuit breakers, I guess is the question. You want the contact is designed different. Vacuum circuit breakers, they do not have these contact that swipes or wipes inside another contact. Vacuum circuit breakers are basically two discs that are compressed, or they touch, or they go together, and there's a mechanism that compresses those two contacts. So there's not going to be a displacement of one contact inside the other one. So dynamic resistance measurement is not going to work here. What I also want to mention is that if you are thinking about these medium voltage GIS, where you have these other breakers that you don't have access, that one DCM won't work, or DRM won't work there as well. You just need to detect the voltage coming or disappearing or showing up.
All right, thank you, Volney. We have time for one last question, and I'm going to direct that over to Daniel. Daniel, is it possible to test SRM or DRM with both sides grounded? If yes, how accurate is it compared to one side grounded?
Yes, you can use this method with both sides grounded. And how accurate, and would you need an extra accessory like a CT? Like I think Volney showed a slide on using this technique to test the contact resistance on a GIS breaker. It depends exactly again on the application, and basically boils down to that circuit to ground. How is that resistance compared to the resistance of the breaker under test? In this specific situation, for example, the one you guys are looking in the slide, sometimes that resistance is even lower than the actual circuit breaker, right? So if we inject the current, we'll get equally divided, or the majority of the current will go through ground. So that will be actually very affected. In that case, you need an extra accessory, a CT, to measure that current going through the ground circuit, and thus the circuit breaker contact resistance can be determined. On other applications, for example, in a death tank breaker, where the contact system, right, what you want to measure, the resistance is many times lower, or sometimes an order of magnitude lower than the resistance of the ground circuit, then you don't need the extra accessory. You can test just like Volney is showing, just connect with the SDRM box, and you will get an accurate measurement.
All right, thank you, Daniel. It looks like that's all the time we have for questions today. We apologize if we didn't get to your questions live, but we will be trying to follow up with you offline in the following weeks. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. Once again, I'd like to thank you all for attending, and I hope you all have a great weekend.